things happen. Okay. Uh, what does it mean when we say something happens randomly? Well, it happens by chance. That's why we call it random chance. Okay, the probability of a simple event is a ratio. It compares the number of outcomes that you're looking for versus the number of total possible outcomes. Like, for example, this six-sided die. Let's look at the total number of outcomes. Oh, there's 6 outcomes. What's the chance of me rolling a 1? What's the probability of rolling a 1? Well, that's 1 outcome out of 6 equally likely outcomes. Now, random outcomes don't have to be equally likely. Like, for example, I could take this die and I could put a 6 on every single face. Okay? That would mean that the probability of rolling a 6 would be 6 equally likely faces out of 6 equally likely faces. The probability of rolling a 1 would be 0 of the equally likely faces out of 6. That would be 0. Now, 0 means that an event is impossible. If the probability is 0, it can never happen. If the probability is 1, it always happens. Now, if you have 2 events that are only A or B, so in other words, you have to get one of them, then the probability of them put together is 1. You always get something, so it's sure that you will get an outcome. Like, say, PA plus P not A. The probability of outcome A plus the probability that you get not outcome A is equal to 1. Because you will always get either A or not A. Okay, let's do some examples. What's the probability of rolling a multiple of 3 on a number cube, also known as a die, marked with 1, 2, 3, 4, 5, and 6 on its faces? Usually you will notice that in higher grades you just call this a 6-sided die, where it's assumed, unless otherwise stated, that it's marked with 1, 2, 3, 4, 5, and 6. So a multiple of 3. Well, probability of multiple of 3 is equal to outcomes that are multiples of 3 over all outcomes. Now, as you advance in grade level, you will often omit this line for simple problems. However, if you have difficulty working out a problem, you should still write out your entire thought process so that either you're going to go, and suddenly notice something, or your teacher at least knows that you have some idea of what you are doing. Otherwise, the teacher is like, okay, so he started up here and then suddenly he's down here. I have no idea what this kid did, but it's wrong, so therefore, no marks. As opposed to, well, okay, I can see that he follows this train of thought, which is correct, but here he made a little mistake, so I'll give him, like, I don't know, half a mark or something. All right, this of course depends on your regional marking schemes. In some places they don't give partial grades, although these places are becoming increasingly rare. Anyway, what are the outcomes that are multiples of 3? Well, 3 and 6, so there are 2 of them. Now, unless we're told otherwise, we assume that a die, or a number cube as they call it, has all faces equally likely to show up. We all know that equally likely is a bit theoretical, because if you look at this die, you see that there are dimples in it for each of the dots. So the weight distribution, or mass distribution, if you like physics, is not in fact exactly the same on all its faces. That tells us that the die is actually not going to be in fact fair. But hey, guys, in theory and reality are the same, okay? So in theory, a six-sided die is equally likely to come up on all six faces. In theory, if you flip a coin, it's equally likely to land heads or tails. In theory, if you calculate the chance of having a boy or a girl, it's 1-to-1, in theory. In practice, this is not in fact the case, as you will learn if you do a little bit of investigating or take some science classes. Well, so there are two outcomes that are what we want. So multiples of 3. Okay, how many outcomes are there? Well, how many equally likely outcomes are there? There are 6. So, what does this simplify to? 2/6 simplifies to 1/3. So if we have to write a statement, we would say the probability of rolling a multiple of 3 is 1/3. Okay? Basically, restate part of the question and put in your answer. Now for another example, what is the probability of not rolling a multiple of 3? Well, the probability of not multiple of 3 is equal to 1 minus the probability of multiple of 3 of 3. Okay. We found that to be 1/3 just now. So it's 1 minus 1/3, which is equal to 2/3. Of course, technically, we could have gone with the same number of outcomes that are not multiples of 3 divided by total number of outcomes, which would still have given us the same answer of 2/3, or rather 4/6 first. Now what happens if you are told that the die was numbered 1, 2, 3, 4, 5, and 5? Well, because we assumed each of those outcomes were the same probability, your answer to not multiple of 3 would be 5 outcomes out of 6. The two 5s would be different outcomes. This is important. Exercises. A set of 30 cards is numbered 1, 2, 3, all the way to 30. So suppose you pick a card at random without looking. Find the probability of each event and write as a fraction in simplest form. So the chance that you get 12 is equal to number of outcomes equaling 12 over total number of outcomes. For time purposes, and because you will be very bored if you keep on watching me write out the same old thing repeatedly, if you need a reminder of how it works, I will state it, but I will skip directly to the next step, as you will probably do too for most relatively straightforward questions. This means that when we get to somewhat more sophisticated examples, I will in fact be writing the words out. But for now, this is one outcome, that's 12, out of a total of 30 outcomes in the 30 cards. Now, for probability of 2 or 3, That's going to be, there are two cards that are numbered 2 or 3. Which means, looking at 2 over 30, which is equal to 1 over 15. Now the chance that you get an odd number, there are, how many odd numbers here? There are 15 odd numbers. Because we alternated odds and evens, and we started on an odd and ended on an even. So there's an odd, even, odd, even. There are full pairs, okay? This is sometimes used as a trick question if you say had cards that were numbered 1 to 29. Guys, it's not going to be 1/2 being odd if you have, well, not the same number of odds and evens. So, this is, we have 15 odd numbers. Out of 30 numbers, which is 1/2. The probability of getting a multiple of 5. Hey guys, if we had ended this on, say, 29 or 32 or whatever, this would not be just 1/5, but in this case, we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then 26 to 30 at the end. So we have full sets. So you can immediately jump to, oh, it's going to be 1/5. Because getting tripped up the next time you have to deal with a question that's something like, oh, the cards are numbered from 3 to 2003 is nasty business. Don't get tripped up. Actually think over the number of outcomes. Or actually write out number of multiples of 5 over total number of outcomes. Now, we won't do that for time, but, well. So multiples of 5. How many are there? We have 5, 10, 15, 20, 25, 30. Okay, 6. This is not actually what the convention for counting, finger counting to 6 is, but I've been using it for so long that I just kind of don't bother. Yeah, okay, multiples of 5. It's going to be 6 out of 30. And the chance is equal to 1/5. Okay, the chance of not a multiple of 5. This is a complementary event to being a multiple of 5, and therefore it's equal to 1 minus p multiple of 5. Which is equal to 1 minus 1/5, which is equal to 4/5. Now, the chance of it being less than or equal to 10, we started at 1 and we ended at 30. That means we would be looking at the first 10 numbers out of all 30 numbers, because we were counting one by one, as opposed to 1, 3, 5, 7, 9, and so on. Okay. What you're actually counting is very important. Don't accidentally forget that you're, say, not counting every number. That would be very awkward indeed. So this is 1/3. Okay. Oh well, that's it for this section. The next section is sample spaces. If you have a game, in mathematics terms, a game is pretty much any sort of probabilistic event between two players. Or you can be talking about any activity they choose to engage together in, such as tic-tac-toe. There may or may not be a dominant strategy to the game. However, a fair game is one where players of equal skill have an equal chance of winning. Now, for probability purposes, this generally means the outcome of who wins like wins as defined by a win condition, is entirely up to chance and is equal between all players. This does not mean that the chance has to be particularly high. For example, a lottery is, in theory, a fair game because people just randomly guess combinations of numbers, and then some combination of numbers is randomly picked from the pool. The chance of anybody getting the right combination is, in theory, the same. Of course, this doesn't mean that anyone actually wins. Like, even on a very small lottery, like say a 6-sided die, if you tell each player to pick one number and you roll the die, it could be that there's a 2/3 chance, if they pick different numbers, that both players lose. However, there is a 1/6 chance that either player wins. That is a fair game. For this grade level, at least in this curricula, you have tree diagrams or tables, which, I mean, yes, they're good for actually visually showing you the sample space, i.e. all the possible outcomes, and they kind of help make sure that you don't miscount things, but I am not a fan. Well, no use complaining about it. You will still eventually have to do some of these problems, so we might as well know how to do them, right? Okay, so for a tree diagram, often, but not always, you will see each decision level labeled. If you have a big tree diagram with many decision levels, many splitting levels, so many columns, you will want the columns to be labeled. Here, well, yeah, let's do so. Okay. Color. Start at the beginning. Brown and black. Now, each of these we can choose small or large size. I realize that to many of us, this makes very little sense. Do you want to know why? It's because when you're buying a watch, for most people, the size, i.e. whether it actually fits on your wrist, is rather more important than the color. At least for most sensible people. Yeah, okay, that kind of is a problem, because common sense is a bit of a joke, because it's not common. Well, anyway, the number of color size combinations that are possible, there are 4 combinations. Now, wait a second, guys. If you look at this diagram from afar, it's like, wait, what? Did you miss some branches? That's why usually there's some sort of divider between the column labels and the actual columns. So now we write 4 combos. Okay, guys, if we wanted to make a table version of this, there are 2 style options we can have. Like say brown, and size small, large. This version is where you write out every single outcome on both sides, okay? But you can also adopt a different style where, say you have this, black, and then small, large. Now this here these are supposed to be two separate versions, okay? I'm just showing half of each so that you have an idea of what each one looks like. If we went with this style, up here we would only write brown once in a big unified box. On a spreadsheet, you can get this by using the Merge Cells tool. Now, example 2. The chance of having either a boy or a girl is 50% in theory. In reality, this is not true. What is the probability of the Smiths having 2 girls? Well, first child is boy or a girl. Yes, intersex people exist, but since we're already going to the rounding error level of 50% boys, which is totally false, the real ratio is around 105 boys per 100 girls. So everything else just kind of disappears into the rounding error. And the second child is here. And we divide this up. Okay, so 1 of 4 outcomes. Now the important thing here is that 50%, that's 0.5, and then 0.5 again. Now, there's actually different conventions for how you label these, because I'm going by this is out of all the ones that went here, so out of 1 convention. Another one is that if you say 0.5, so 50% go here, and this is also evenly divided, you have to label each of these 25% or 0.25, so that everything traces back to 1 at the beginning. Yeah. So be careful what convention you guys use in your area. In some areas, you don't even bother labeling the things if the probability of each dichotomy is considered equal. A dichotomy is where it splits into 2 paths, or trichotomy. So just if the probability of every single divide at every single division point is considered equal, you can just not even label these things. Okay, this is multiplicative labeling. You can also have additive labeling. The terminology for those label types may also vary from area to area. The probability of the Smiths having 2 girls is 1/2 times 1/2. So probability 2 girls, or G comma G, is equal to 1/2 times 1/2. Which is equal to 1/4. All right, let's do some exercises. For each of these situations, make a tree diagram or table to show the sample space. Then give the total number of outcomes. It doesn't say anything about probability of any outcome. So let's say we're choosing an outfit from a green shirt, blue shirt, or a red shirt, and black pants or blue pants. So I am going to choose the pants first. Why? Well, in most areas, you are less likely to be arrested if you only go outside wearing your pants compared to only going outside wearing a shirt. Yeah, try not to do either of these things if you can avoid it, but another reason, the true reason, is that black and blue I actually have to write in full, unlike G, B, and R for green, blue, and red. So I'm saving us some time and effort watching. Pants and shirts. Or rather, shirt, because you're only wearing one, I think. Green, blue, and red from black pants. And from blue pants, you also have green, blue, and red. So, in total, there are how many outcomes? There are 6 outcomes. We could have found this from going, oh, we had 2 choices for pants, and each of them has 3 choices for shirts, therefore we just multiply. Yeah, that's what we'll do a little later when we get to the counting principle. So let's choose a vowel from the word counting. That means O, U, or I. And a consonant from the word prime, which is P, R, or M. So, the vowel, we're going to have O, U, and I. We, as in yes in French. How interesting. Anyway. And for the consonant, we would have P, R, and M for each one of these. Okay, P, R, and M. P, R, and M. Perhaps we could have made this tree diagram a little bit more compact and not needed to draw such long lines. Yeah, do actually consider this sort of thing when you're making your tree diagrams, because otherwise, if you have a whole bunch of really long lines that come close together, you might actually miscount them if you don't count at the end for whatever reason, which of course is not recommended. So we have 3 vowels, each of which we can choose 3 consonants. 3 times 3 is 9, right? So 9 outcomes. Well, how do we do this without drawing all these irritatingly huge and tedious diagrams? That is the stuff of the next section. Now, the fundamental counting principle is that if you have 2 events, you can multiply the number of ways each of them can occur for how many ways the 2 events can occur in total. For example, if you flip a coin and then roll a die, well, for every outcome of the coin, so heads or tails, there are 6 outcomes for your die. So there's heads and 6 outcomes, and tails and 6 outcomes. So that's 2 times 6 for your total, which is 12. If you roll a die twice, or roll 2 die one after the other, you can have how many outcomes? No, this is not the total of 2 die. That's different. This is a numbered set that's like, say, 1, 1, or 1, 2, all the way to, say, 6, 6. 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 2, 1, 2, 2, 2, 3, 2. Well, you get the idea. So, instead of drawing a gigantic tree diagram, we can just multiply the number of ways the events can occur to get how many ways they can occur in order. Now, let's say Andy has 5 shirts, 3 pairs of pants, and 6 pairs of socks. How many different outfits can Andy choose with a shirt, pair of pants, and pair of socks? You know what? This question could be much more amusing if it was, say, 3 pants and 6 socks. And then it's how many different outfits can Andy choose? That would require you apply a little common sense and go, you can have only pairs of socks. Like, no, if you want a full outfit that includes socks, you want pairs of socks. And out of 6 pairs of socks, there are 6 choices for your first sock and 5 choices for your second sock. Now, does left and right matter? Yeah, actually it does. But that stuff is for combinations, which we'll get to later. So, this number of outfits equals number of shirts times number of pants times number of pairs of socks. So he has 5 choices for his shirt times 3 choices for his pants because they are not dependent on each other. For every shirt, he has 3 choices for pants. And every combination of shirt and pants, he has 6 choices for his pairs of socks. And this would come out to 90. So he can make 90 outfits. With how many items of clothing? Well, if we count a pair of socks as 1 item of clothing, this would be 14 items of clothing. As you can see, you don't need that many different items of clothing to make many different outfits. So whenever somebody decides to whine that they have nothing to wear, that just indicates that they are lacking in creativity. Usually. I mean, yes, there are actually people who have very few outfits. Such is life. Okay. The statement would be, Andy can choose 90 different outfits. We'll skip writing that, though. Exercises. Use the fundamental counting principle to find the total number of outcomes in each situation. Say we're rolling 2 number cubes, aka 2 die. Wait, no. It's 2 dice. That's a plural. Okay. Anyway, that's... By default, we consider number cubes... Wait. How many faces does a cube have? Oh, it has 6 faces. That's actually why they often use number cubes nowadays instead of dice. Because although the usual dice you deal with have 6 faces, there are such things as 4-sided dice. Those are tetrahedrons. They have 4 equilateral triangles. And there are also 8-sided die, where you have 2 square-based pyramids joined together at the square base. And then you have stuff like 20-sided die. Yeah, this stuff gets complicated real quick. So yeah, that's why they use number cubes. Well, anyway, the total number of outcomes are 6 outcomes for your first number cube, or 6-sided die, times 6 outcomes possible for your second one is equal to 36. Tossing 3 coins, you can have 2 outcomes for your first coin, times 2 outcomes for your second coin, times 2 outcomes for your third coin, and that's 8 total outcomes. Suppose we're picking 1 consonant and 1 vowel. We're going by the A-E-I-O-U convention, even though we know that Y is sometimes a vowel. So, assuming this is actually important, A-E-I-O-U vowels, we would have 21 consonants times 5 vowels. And that gives us 105 combinations. Now let's say we have to make a computer, or maybe a cell phone. Cell phones don't have hard drives, we don't call them that at least. So a computer, and we have to choose one of 3 processor speeds, 2 sizes of memory, and 4 sizes of hard drive. As far as I'm concerned, for processor speeds, there's only one option really, and that's the highest one you can get. But yeah, economy is kind of important, depending on what you're using this computer for, which means this is going to be 3 processor speeds times 2 sizes of memory times 4 sizes of hard drive. Although why you would put a huge hard drive or huge memory with the lowest processor speed you can get, I have no idea. Anyway, the total is 2 times 3 is 6, 4 times 6 is 24. Now, let's say you're choosing a 4, 6, or 8-cylinder engine, so 3 engine choices times 2 drive choices. This would give you 6 combinations, or 6 outcomes. Yeah, best not use the term combinations too much because we're going to be using that later for a more technical idea. All right, rolling 2 number cubes and tossing 2 coins. If we're rolling 2 number cubes, that's going to be 6 times 6, and then tossing 2 coins times 2 times 2. This is equal to 144. Let's say that we have to choose a color from 4 colors and a number from 4 to 10. 4 to 10 is 7 numbers. It's not 10 minus 4. Why isn't it 10 minus 4? Well, let's say we have numbers from 1 to 10. Oh, that's 10 numbers, right? Clearly, counting from 1 to 10 is 10 numbers. Okay, how many are we taking out? Oh, we're taking out 1, 2, and 3. We're not taking out 1, 2, 3, and 4. So this is 7 numbers. 7 numbers. When you get a string of numbers that don't start with 1 and are counting 1 by 1, you take the biggest one, so a string of consecutive numbers, you take the biggest one, you subtract the smallest one, and then you add 1 to get the total number of numbers you have. So how many numbers do you have? 10 minus 4 plus 1. Because if you minus 4, you also include the 4 in what you removed. And that's not true. So you have to add 1. So choosing a color from 4 colors gives you 4 choices times 7 choices of number, which gives you 28 outcomes in total. Okay then, what happens if we need to make a list of objects, such as out of 20 competitors, how many ways can people come into the top 5? Well, the order matters. First place is not the same as second place, and that's not the same as third place, or fourth place, or fifth place. So, if we want to find how many ways they can be arranged, we can use the fundamental counting principle. There's a reason why these examples seem to just be multiplication problems. Consider this. Let's say we have 5 people and we need to decide how many ways they can be lined up. Well, there are 5 choices for our first person in the line, and then there's 4 remaining choices for the second person. So for each choice of first person, there's 4 choices of second person. And for each combination of that, or rather each permutation of that, because combinations are different mathematically, each permutation of that, we have 3 choices for the third person. And then we have 2 choices for the fourth person. And the last person goes in the 5th place. This is the sort of number you would get if you were picking 5 items for 5 sequential places, or 5 places where the order matters. This is 5 pick 5. Notations may vary, but this is the way you can see it on most North American calculators. NPR is the symbol they use. Anyway, this value is equal to 5 times 4 times 3 times 2 times 1. 5 times 2 is 10. Okay, 4 times 3 is 12. Therefore, this is 120. Now let's look at 4 times 3 times 2 times 1 times 2 times 1. Well, 2 times 4 is 8. 2 times 3 is 6. 6 times 8 is 48. All right. What sort of situation would this problem be like? Well, let's say you had 4 people who you knew qualified for the top 4 places in a contest, and you have 2 people who qualified for 5th and 6th place, but you forgot who came where. How many orders could they have possibly come in? Well, for the first 4 places, you have to pick the first person. You have 4 choices. Second person, you have 3 remaining choices for every choice of first person. So 4 times 3. And then third, times 2, because you have 2 choices left. And the fourth, times 1. And then, for every permutation of the first 4 people, you can choose between 2 people for 5th place and 1 person for the 6th place. This would be 2 permutations multiplied together. This would be 4, pick 4 times, or multiply, the cross multiply if you want. Cross multiplication and dot multiplication are in fact different, but they're not really relevant to us for now. They're different when it comes to vectors, though, which you'll deal with later, much later. All right, how many ways can 4 different books be arranged on a bookshelf? Well, you have 4 choices for your first book. Okay, and for every single choice of first book, you have 3 choices for your second book out of the 3 remaining books. And then for every permutation of those 2, you have 2 choices for your third book and 1 choice for your last book. And this is equal to 24 ways. Let's do some exercises. Find the value of each of the expressions here or solve. This 3 times 2 times 1 is 6, as I hope we are familiar. 7 times 6 times 5 times 4 times 3 times 2 times 1. Well, we know that 5 times 2 is 10, 4 times 3 is 12, 6 times 7 is 42, so it's 42 times 120. If you had a calculator, this could be done with the factorial sign, because this is 7 factorial, which is equal to 7 times 6 times 5 times ... times 1. Factorial symbol, which on your calculator should be given like this, means multiplying from that whole number down consecutively smaller whole numbers all the way to 1. But we're trying to avoid using calculators if possible, because there are plenty of occasions, such as contests, where you're not allowed to use calculators. So 2 times 2 is 4, 4 times 2 is 8, so this is going to be 840. And the 1, that comes out to 2, and you carry 1, and you end up with 5040. Okay, then, what happens if you do 6 times 5 times 4 times 3 times 2 times 1, and then times 3 times 2 times 1? Well, this is actually equal to 6 factorial 3 factorial. But that's not very helpful to us, is it? Yeah, we actually want to evaluate the actual numbers. 6 factorial, we know 5 factorial is 120. 6 factorial is 120 times 6, which is going to be 720. 3 factorial is 6. Therefore, this is going to be 0, 2, and 42 up there. Okay, 9 times 8 times 7. would be what happens if instead of, say, 6 pick 6 times 3 pick 3. Instead of this, we would be looking at 9 pick 3. Why is this the case? Well, for the first choice, we have 9 choices to pick from. For the second one, we have 8 remaining choices for each of our first choices. And then for the third one, we have 7 remaining choices. And the rest, we don't care. And this gives us 72 times 7. That's 504. Okay. How many ways can you arrange the letters in the word group? There are 5 letters. So this is equal to 5 pick 5, which is 5 times 4 times 3 times 2 times 1, or 5 factorial, which is 120. There are 120 ways that you can arrange the letters in the word group. That's what you can write in a statement. Or you can arrange the letters in 120 ways if you want to write a little less. How many different 4-digit numbers can be created if no digit can be repeated? Remember, a multi-digit number, in other words, if you have a 1-digit number, yeah, it could just be 0. Okay. But if you have a 2-digit number, you can't have 05. No. That's not a 2-digit number anymore. So a multi-digit number cannot begin with 0. That means for the first digit, you can have 9 choices for first digit. And multiplied by, what about your second digit? Well, from 0 to 9 is 10 different numbers that you could use, but you already used one for your first digit, so you have 9 left. And then for your third digit, you've already used up 2 of your digits, so you end up with 8 times 7, which leaves you with, it's 504 times 9, because we calculated this part up there. 504 times 9 is 4536. So, statement is 4536 numbers. Well, I mean, you might want to write different numbers if you like. Can be created. Hurrah. Okay, well, that's it for this section. Now, we actually use the term combination correctly for once, we hope, right? So, combinations are arrangements or listings where the order is not important. So, let's say we had 5 people who we wanted to choose for 5 different positions. The order there is important because they're going to different positions. But let's say we have 5 people and we want to make a group of 5 people who are all the same position. There's exactly one way to do that, and it's to choose all of them. That's why, instead of pick for permutations, we use choose for combinations. You see this on your calculator as n choose r. So out of n items, you are choosing r items. Now you divide the number of permutations of the set by the number of ways each smaller set can be arranged. Now when you were doing permutations, n pick r is equal to n factorial divided by n minus r factorial. Why is this? Well, let's say that we have 9 and we're picking 3. Okay, so we know that's going to be 9 times 8 times 7. Oh, wait a second. What's a 9 minus 3? Oh, that's 6. Oh, so it was 9 factorial, so 9 times 8 times 7 times 6 times all the way to 1, divided by 6 times 5 times all the way to 1. So that canceled out all the rest after the 9 times 8 times 7. This is the algebraic expression for n pick r. Okay, well, what's n choose r then? Well, we know that we're dividing the number of permutations by the number of ways the internal arrangements of the set can go. Well, let's say we don't actually care which one got picked first out of these 9 things, and which one got picked second, and which one got picked third. Okay. So, out of those 3 things, how many orders could they have been picked in? Out of every set of those 3 things. There are 3 choices that could have gone first, and there are 2 choices that could have been picked second, and 1 choice that could have been picked third. Then, that would be 3 times 2 times 1. But hey, we just said order didn't matter, so we got to get rid of all the different orders. That means NCR is n factorial divided by n minus r factorial, and divided again by r factorial. Because r factorial is the number of ways you could have picked r items out of r. We'll see how that works here, okay? So, we know that Jill could pick from 8 items for her first topic. This is 8, choose 3, by the way. So we know she could have picked 8 items for her first topic, and 7 items for her second topic, and 6 items for her third topic. But hey, what if she picked them in different orders? Like she picked the same 3 topics but in different orders. Well, there were 3 ways that one of the topics could have shown up. Like say topic, let's call these topics A, B, C, D, E, F, G, and H, okay? Let's say she ended up picking topic A, B, C. If we consider ABC to be the same as CBA or BAC or BCA, then how many ways could those have been arranged? Well, there would have been 3 choices for your first one, and 2 choices for your second one, and 1 choice for your third one. 6 ways. There are 6 ways to pick between A, B, C, or any 3 items, if you want to pick 3, or all of them. Now, if we get rid of all the variations, you end up with just A, B, C unordered. And same goes for every other set of 3 things you could have chosen. So, what is this part? What is 8 times 7 times 6? Oh, hey, that's just what we did up here. That's 8 factorial divided by 5 factorial. Why do we need to bother with these formulas then? Well, guess what happens when you start doing bigger numbers, like lotteries. When you start doing lottery numbers, you end up being like 47 times 46 times 45. No, let's not mash so many buttons. 47 factorial divided by 40 factorial. And then divided by 7 factorial because the order doesn't matter. That's way faster than going 47 times 46 times 45 times 44 all the way to whatever number you stop on. And then it's easy to mess it up. Okay, then. What happens here? Oh, we cancel out the 6. Hurrah! 7 times 8 is 56. So, Jill could choose 56 different 3-topic groups. For this grade level, it's okay if you just think of it like this sort of way, where you don't bother with quite so many algebraic formulas, but eventually you'll have to learn these. Just because you really don't want to do a lottery problem and be like, oh, I accidentally got a number that's 40 times bigger than it was supposed to be because I pressed my calculator buttons for too long. Yeah, that's not a good time for anybody involved. So don't. All right. Example 2. On a quiz, you are allowed to answer any 4 out of the 6 questions. How many ways can you choose the questions? What do you mean on this quiz you're only allowed to answer any 4 out of the 6? Bah, I'm sure there's enough time to answer all of them. Well then. How many ways can we choose the questions? This is 6, choose 4. Okay. So, we have 6 times 5 times 4 times 3 for our choice of the questions in order that we're answering, and then divided by all the ways they could have been ordered. Times 2 times 1. Right, we can already cancel out part of this. We can actually cancel further if we like. And this is 15. So there are 15 ways we can choose to answer the questions. Now there's an important issue here. What happens if we were asked, you are allowed to choose to not answer any 2 of the 6 questions? That would be 6, choose 2. And we would have 6 times 5 divided by 2 times 1, and we would come out to exactly the same number. This is a rule of combinations. N choose R is equal to N choose N minus R. Now, let's say we want to have 5 cars entering a parking lot with only 3 empty spaces. In how many ways can these spaces be filled? First of all, don't troll teachers by going, these 5 are all micro cars, so you can park 2 in each empty space. This does not go over well with teachers. Now 5 cars, and only 3 of them can end up parking here. So if we pick them in order, it would be 5 times 4 times 3. And we know that in reality parking spaces are not made equal because they are different distances from, say, the exit of the parking lot or the entrance of wherever you want to go, to whatever businesses the parking lot serves, etc. But let's say they're equal, so we have a problem here. In how many ways can these spaces be filled? This is not a question that actually specifies whether the order of the filling of the parking spaces matters, because in reality we know parking spaces are not equal. So should we be dividing by 3 times 2 times 1? Well, in this case, this is an example problem for combinations, so yeah, we probably should be. It probably means, in how many ways can we choose the cars that actually get parking spaces? Or in how many ways can we choose the cars that have to go somewhere else? You'll find that Canadian textbooks are unfortunately pretty full of, or North American textbooks in general are pretty full of funny questions. Where it's like, technically, no, please don't do technicalities. Most math teachers will not be amused. All right, let's do some exercises. Tell whether each situation represents a permutation or combination, then solve the problem. How many ways can 4 people be chosen from a group of 11? Well, this means just a group of any 4 people. Which means that there's no particular order involved. So this is going to be 11 choose 4, which is equal to 11 times 10 times 9 times 8 over 4 times 3 times 2 times 1. As you can see, even I'm not bothering with the algebraic version because these are relatively small numbers and I don't have a need to pull out a calculator yet. So, the 8's cancel out. This comes down to a 3. So we're looking at 33 times 10 equals 330. That's a lot of ways, even though the group doesn't seem very big. So how many ways can 3 people sit in 4 chairs? I, for one, am very well aware that it's possible for one person to sit in multiple chairs at once. But this is math class, guys. Fewer technicalities, please. So, are these 4 chairs different? Oh, they're not stated to be, so we're assuming they're identical chairs. We're also assuming they're in identical positions because guess what, guys? Having a chair that's the same as another chair, but they're at different corners of a classroom is kind of pretty important. Yeah. But this is math class, and we're not, in fact, trying to shoehorn ourselves here. Therefore, this is 4 choose 3. So we choose 3 of the chairs to have the dubious honor of actually carrying people. 4 times 3 times 2 over 3 times 2 times 1. Why is it 4 ways? I mean, we're choosing 3 chairs out of 4 to actually have people on them. That's the same as choosing the 1 chair out of 4 that doesn't have a person on it. And guess how many ways you can choose 1 chair out of 4? 4 ways. No surprise, I hope. Anyway, how many ways can 2 goldfish be chosen from a tank containing 15 goldfish? Well, whatever these 2 goldfish are being chosen for, the order doesn't in fact matter. It's just a group of 2 goldfish. Therefore, this is 15 choose 2, which is equal to 15 times 14 over 2 times 1, which gives us 15 times 7, or 105. Now, in how many ways can the student council president, vice president, secretary, and treasurer be chosen from 7 candidates? Oof! President, vice president, treasurer, and secretary. Whoa, these are different titles. That means the order that they are chosen matters. So you have 7 pick 4. Which means you're looking at 7 times 6 times 5 times 4. Or, let's do some math. Okay, 7 times 6 is 42. 5 times 4 is 20. 42 times 20, well, 42 times 2 is 84. And times 10, 840. Mental math is strongly recommended for small numbers where you really don't need to button mash on a calculator. Okay, this section. Oh, look. In North America, you will be, well, actually, in the English-speaking world in general, you are often expected to actually act out your questions so that you can visualize them better, as if kids don't know to sit there and imagine. Well, my opinion of this can be of the habit of making kids actually act out problems is best reserved for private occasions. However, well, you kind of are expected to know this stuff in school, which means we still have to, in fact, cover this. Yes, 99% of students hate making spinners or flipping coin experiments or whatever, but they are a thing. Like for this example, you might say use flipping a coin for your shirts, and then you roll a die, and you say 1 and 2 are one set of pants, 3 and 4 are another set of pants, 5 and 6 are the third set of pants. Yeah, you would act this problem out, or you could use a spinner, which is a round piece of paper or just a circle that's drawn with different sectors that are delineated on it, and you put a pin of some sort through the middle, and you put a spinning needle, whatever, or maybe a paper clip on the pin, and you flick it around. Yeah, I know, it's just as terrible as it sounds. Anyway, how many different outfits can he make by wearing one shirt and one pair of pants? However you have to act this out in class, this is going to be 2 times 3 equals 6 outfits. How terrible, I know, right? Now, exercises. Yeah, you may actually have to get in groups of 4 students and actually act out how to line up on 4 different tables. Hopefully these tables will not be too far apart and this will not actually be an exercise for you. Or you might say draw 4 squares and then you move tokens or some other crazy thing that teachers sync up for you guys. But anyway, you actually have to know this sort of thing exists in schools around here. And this is solved by 4 pick 4, because there are 4 choices for your first table's person times 3 choices for your second table's person times 2 choices for your third table's person times 1 choice for your last table's person, which is 24 ways. Hurrah. Now, let's say we flip a coin and we see if it's a good way to predict the gender of the next 5 babies born at a hospital. Let's say that we flip the coin 5 times. How many ways can the next 5 babies born in a hospital be arranged in terms of gender? Oh, that's 2 times 2 times 2 times 2 times 2, or 2 to the 5th power, equals 32 ways. So if you flip your coin for a certain arrangement of heads and tails, one of them representing males and the other one representing females, sorry, but intersex is like your coin lands on edge and stays there, rounding error. Anyway, you would end up with roughly a 1 in 32 chance of actually getting the prediction right, which means no. 1 in 36 odds of being correct. For now we use odds. Usually similarly to just chance, but odds actually mean something different, which we'll learn in much later grades. Right. Do not make a good prediction. Let's say we need to enter 4 runners in the first hurdles heat of 12 heats at the Olympics. The first 2 move on to the next round. Assuming no ties, how many different ways can the 4 runners come in first and second place? Well, for the first place, there are 4 people to pick from. And for the second place, you'll have 3 people left. In other words, 12 ways. Yeah, units are kind of important. Here, we see reality intrude on our theory. In theory, theory and reality are the same. In reality, they are not. So, let's say we want to actually test a game and see what the probabilities look like. Well, the theoretical is the expected chance that an event occurs. Experimental is found using actual testing. Like say this graph, if you roll a number cube 100 times and you end up with this distribution, then your experimental probability of rolling a 3 was experimental of 3 is going to be 16, or number of times, yeah, we should write that down, times 3 actually occurred, divided by total trials. Which is going to be 16 over 100. Or, if you cancel out a bit, it's 4 over 25. Now, your experimental probability does not have to match your theoretical. It doesn't even have to be all that close to your theoretical. For example, if you throw a coin once, you end up with the experimental probability of the outcome you actually got being 1 and the other one being 0. However, if you throw your coin 100,000 times, don't actually try this, please, and you end up finding that you got one outcome, say 51,000 times, and the other one 49,000 times, you would be very right to be suspicious of your coin, because the law of large numbers tells us that as the number of trials increase, the experimental probability should come closer and closer to the theoretical probability. Or rather, the true probability. All right. Let's say we make a telephone poll and we ask 225 people who they plan to vote for in the race for mayor. And the experimental probability of somebody voting for Huare is I'll just use PJ for this. This is equal to the number of people who said they would versus the total number of trials, which happens to be 1/3. How does this relate to his chance of actually being elected? That is actually very complicated. His chance of being elected is not 1/3. Abramson is noticeably higher in experimental probability of someone voting for him. So if all the votes were distributed randomly with this probability distribution, Huarei has a very, very low chance of being elected with this many voters. This is something you will learn rather later in statistics or data management. You will find that the distribution tightens up relative to the overall graph of 0 to 1, so 0% of outcome to 100% this outcome, around your mean value. It will tighten up more the larger your actual number of trials is, assuming that your mean value is actually accurate. Like I said earlier, if you throw a coin 100 times, getting 51 heads and 59 tails is, whatever, it happens. But if you throw it 100,000 times and you get 51,000 heads and 49,000 tails, you'd be like, okay, it's probably not actually 50-50. Yeah. Well, we could also go for a slightly more obvious example, like say throwing a coin 10 times and being like 6 heads, 4 tails, whatever. Throwing it 10,000 times and getting 6,000 heads and 4,000 tails is a, I don't think this is a fair coin. Yeah, so, suppose 5,700 people vote in the election above. How many can be expected to vote for Huarei? Well, expectation is equal to probability times n, or NP. In this case, it's expectation of Huarei voters is equal to total number of voters times the probability of somebody voting for Huarei, which is 5,700 times 1/3. And that is equal to 1,900 people expected to vote for Huarei. Alright, exercises. For exercise 1 to 3, use a graph here of a survey of 150 students asked whether they prefer cats or dogs. I see a lot of people here prefer dogs. What is the probability of a student preferring dogs? Well, P dogs is equal to number of outcomes that are dogs over total trials. I mean, technically it should be n bracket dogs, but we're going to skip over that step because it's pretty obvious here. And we've talked it over already. So what happens if we simplify this a bit? Well, if we divide everything by 6, we would get over 25. And up here, we would get 22. 22 over 25. Now, suppose 100 students were surveyed. How many can be expected to prefer dogs? Well, expectation dogs equals number of trials multiplied by probability dogs, which is going to be 100 times 22 over 25, which is equal to 88. Now, suppose 300 students were surveyed, and how many can be expected to prefer cats? That would be expectation cats equals n times probability of cats, which is going to be 300, 1 minus p dogs. Well then, it's going to be 300 times 1 minus 22 over 25, or 300 times 3 over 25. So, you're looking at 12 times 3, which is 36. So only 36 students out of 300 could be expected to prefer cats. Man, I feel vaguely bad for the cats. Let's say we want to have multiple of these simple events put together. This would be called a compound event. If the outcome of the first event does not affect the outcome of the second, they are called independent events, such as throwing a die and then throwing another die. Or throwing one die twice in a row. The probability of two independent events both occurring can be found by multiplying the probability of each of those events together. Like, say, the probability that I get a 1 on the die and then get a head on a coin. Well, that's 1/6 times 1/2. However, if I say have a bag with names in it, the probability that I draw my name after I've drawn my name the first time without replacing it, that's a dependent event. And if I didn't enter my name more than once, it would be the probability is 0. Those would be dependent events because the outcome of your first event affected the probabilities of your second event. Now let's say we have a coin toss and a row of a number cube. Find the probability of tossing tails and rolling a 5. So this would be probability of T5, which is equal to probability of tails times probability of 5. Because these are independent events. This would be 1/2 times 1/6, which is equal to 1/12. Now, example 2, a bag contains 7 blue, 3 green, and 3 red marbles. If Agnes randomly draws 2 marbles from the bag with replacement, so replacing the first before drawing the second, or replenishing the bag with the same thing, doesn't particularly matter, what is the probability of drawing a green and then a blue marble? This would be probability of green and then blue, which is equal to probability of green multiplied by probability of blue, which is 3 over 13 times 7 over 13, which is 21 over 169. Let's do some exercises. Find the probability of rolling a 2 and then an even number on 2 consecutive rows of a number cube. Well then, this would be P2 even equals probability of 2 times probability of even, which is equal to 1/6 times 3/6, or 1/2. And this would be 1/12. A penny and a dime are tossed. What is the probability that the penny lands on heads and the dime lands on tails? Do these events affect each other's probability? No. Therefore, P H T, that's why I'm not even labeling which one's a penny and which one's a dime, is equal to PH times PT. Now we know coins are not perfectly symmetrical. In reality, this is not actually 1/2, but in theory it is. Okay, 1/2 times 1/2. For mathematical purposes, we generally assume, yeah, these coins are fair. So it's 1/4. The chance that the penny lands on heads and the dime lands on tails, because they are independent events. Now, Laszlo's sock drawer contains 8 blue and 5 black socks. If he randomly pulls out one sock, what is the probability that he picks a blue sock? Well, this actually is not a combination of events. That means we're just looking at 8 over 13. Sometimes teachers will give you questions that don't quite fit what the section is supposed to be about, just to make sure that, hey, are you still paying attention around here? So please do be careful. Well, that's actually it for this chapter. So see you next chapter.